Hi everyone. I'm Lucian Wishick, Program Manager on the VB C# F# language team. So far at TechEd, lots of people, myself included, have been talking about how to use asynchronous APIs. Now I wanted to talk about how to create asynchronous APIs in libraries. When I say library, that makes it sound grand. I figure every time you factor out your code into a reusable method in your app, you're making a small library. And the lessons in this talk will apply for small-scale libraries like that, all the way up to a NuGet package that's used by everyone in the world. The body of this talk has got three main lessons. First, that library methods should not lie. That is, if the method looks async, if it's got an async signature, then it should be async under the hood. We'll talk more about that later. The next thing will be about using configure await of false, which is a habit that you should get into for all of your library APIs. And the third thing, I'm going to be talking about perf of async methods. When is it important to worry about perf, and what optimizations are in place, and what can you use? But before getting into those, I think there are some foundational concepts that we need to get clear on. And I'm really sorry at this stage, because every single async talk you go to starts with someone standing up here defining what they mean by async, and this is going to be another one. But this one's important for library writing, right? Because this is going to affect how you architect and expose and how you choose which APIs to expose as async methods from your library. And the thing is, as I see it, there are two ways of thinking about asynchrony. The first way of thinking about it is just from the signature. Like, if I invoke a method foo, my expectation is that it's going to perform something here and now on the current thread, and it won't return till it's finished. If I invoke something using var task equals foo async, I expect that I'm initiating something here and now. I expect that I will regain control immediately to execute somewhere else. So that's what I understand by async by looking at the signature. The complete other side of what we mean by async is looking at the implementation. A synchronous implementation is one that burns a CPU core solidly while it runs. That one obviously burns the core solidly for a while. An asynchronous implementation is one that only touches the CPU lightly. Most of its work is kind of scheduling the next piece of work to be done after a certain event arises or a certain long-running operation has finished. And it's your job, really, as library authors, to make sure that these two things stay in sync. Because when people use your libraries, that's what they're going to expect of you. That previous slide was a bit too abstract. I'm really a concrete person. I wanted to flesh it out with some really concrete, tangible examples. Here, my library method is going to pause for 10 seconds and then print hello. Okay, it's not much of a library method, but hey, it's a start. I'm going to start with one. Right, it's a stupid method. Don't do this at home, please. But what this code is doing is it's just spinning. It's burning the CPU for 10 seconds in an idle loop before printing to the console. And this clearly is synchronous through and through. Its signature looks synchronous, and its implementation is synchronous. So that's good. How about asynchronous? Here's one where the signature looks asynchronous. It returns a task. It's got the word async at the end of it. And its implementation, let's follow through its implementation. What it's doing here is creating a new task completion source, and then it's doing new timer, because it's going to schedule work to happen after 10 seconds, and then it's just going to return a task that it generated, and then after 10 seconds, it's going to print out. So it's very clear that very little CPU work is happening. All of the work is doing scheduling. Actually, we'd never write it this way, of course. What we'd write is public static async task, and we can use await. This is almost identical to the code I showed you before under the hoods. They're doing just the same things. And this one, I call it true async, because the signature looks async and the implementation underneath is async. Okay, so far so good. Let's look at another one. I made this slide with 4 quadrants. Maybe you can see what's coming next. In this one, pause print async. It's queuing a lambda onto the thread pool, and the lambda just calls this pause print method to the left. So this one, when we invoke it, it looks asynchronous, and we're getting back a task, but it's sure as heck going to be burning up a CPU core. Not going to be burning up the caller's CPU core, it's going to be burning up a different thread, but it's still burning it up. I wouldn't write it like this, of course. I'd use task.run, which is the new thing we introduced in .NET 4.5. But this is doing exactly the same thing, scheduling some work to run on the thread pool thread. There's something fishy about this, isn't it? The fact that it looks async on the surface, it smells async, but underneath it's got a sync implementation. It's almost as if this library API has deceived me. It's been lying to me about how it's implemented. Let's look at the final quadrant, pause print down here. What this is doing is it does task T equals pause print async. So it's kicking off my true async implementation underneath, but then it's just waiting for it. It's doing a blocking call, blocking the thread until the async implementation is finished. This one's also pretty fishy. I mean, it looks synchronous, it smells synchronous from the outside from looking at its signature, but under the hood, it's using asynchronous techniques. I want to focus for a bit on the right-hand column. I want to talk about when is this right-hand column appropriate and which of the two things, using a thread or true async, is appropriate. It's important for us to first be clear on what scenarios they're important for, and after we're clear on that, then we can start addressing whether it should be the library method that's doing them or the caller that's doing them. So, question, when to use async? When to use that right-hand column on the previous slide? One reason why we want async is to offload work. Like, we might want to, we're in a UI, a desktop application, a XAML application. We want to do some CPU-bound work on a background thread to avoid tying up the UI. So really, we want to offload some work to a different thread, and we're using task.run. And this here, it's essential for us to use task.run for this purpose. No way around it. Another case where we want to do offloading is kind of the mirror image of that. If we're currently executing code on a thread pool thread, on a background thread, but we want to update the UI, then I do dispatcher.invoke async to offload my work from the background thread onto the UI thread, because only the UI thread, in most cases, is allowed to update the UI. So again, we're using task.run or dispatcher.invoke async or that kind of thing to achieve offloading. Another reason why I want to use async is for concurrency, so I can start multiple operations. Now, it might be one thing, sorry, I meant to say on this side, is that task.run is an appropriate thing to use for these reasons, but it's not generally going to be done by your library. You're going to leave it up to the caller of your library to do the task.run, and we'll see why with a practical example. The next case of wanting asynchrony is for concurrency, where we really want to say, start multiple operations so they can all run concurrently. And if those operations are CPU bound, then we're going to use task.run or parallel.forEach to start them on background threads. If they're implemented by true async, then we can just start them concurrently by launching one task after another, and not awaiting till they're all done. So in this case, task.run and true async are both ways of achieving this goal, but once again, task.run is not something we're going to be using within our library methods, and once again, we'll see why that is. The final reason, and I really want to draw a solid line under it, why people use async is for scalability. Mainly they're thinking, on the server. They want scalability. They don't want resources. They don't want to use, and one of the resources is threads. They don't want to waste threads that they don't want to use. And it was very clear that task.run was using a thread. Therefore, it's very clear that task.run has no place on a server workload if you're aiming for high scalability. The only thing that is appropriate for the server is true async, where it's async all the way through. Well, actually, I just want to flesh this out with an example to make it really solid. Suppose my server can handle properly up to 1,000 threads at a time. And suppose each request is handled by just a single thread. Maybe it's using true async, but still just using a single thread. Then I can handle 1,000 requests at a time. But if each request uses task.run and therefore uses 2 threads, then my server can only manage 500 requests at a time. So I've wasted my scalability through this use of task.run. I have not bought anything at all. So that's why we're not going to be using it. What I want when you write a general purpose library is this. Think to yourself, is my library going to ever be used by someone on a server? If so, I am not going to use task.run. I'm only going to use true async. If I'm only going to be used by desktop apps, then I might consider using these, but there are some caveats that we have to think about. And we'll see those pretty soon. I want to sum this up as a message from the library developer. That is that your library should not lie. What we've said is that if your signature looks synchronous, then your implementation should be synchronous with none of this .wait blocking nonsense. If your signature looks asynchronous, then its implementation should generally be true asynchronous. For the user of your API, the name and the return type are going to be the clues as to what they expect of it. Just what do they expect of it? Well, the user looks at your API, he thinks, hey, this method's name ends with async, so what does he think? So calling it won't spawn any new threads in my server app. That's what your user is going to expect. He's also going to expect, it's async. That means I can parallelize it just by spawning it multiple times, initiating it multiple times, one after the other, without waiting for them all to finish. And you have to ask yourself, when you're writing your library method, are these expectations true for the methods I've written? Let's see a sample. I'm going to show you a contrary example, one that is using task.run inside itself, and I'm going to show where that's hurting. So let's go to this. We can see that okay. I'm going to have several demos in this talk, and I'm just going to start here at the first one. Go to definition. In this demo, I'm just going to do a few lines of code to pop up a completely minimal WinForms application. The reason is I wanted to show you a demo that had something to do with a UI program, but I didn't want all the guff associated with a full-blown UI application. So these in a console app is just the bare minimum you need to spin up a WinForms application. And what I wanted to show you was a library method and using the library method. But the thing is, if I'm doing this, I have to show you the user's code at the top level, I have to show you the library code in the middle, and I have to show you the operating system code at the bottom, or the framework code that my library is using. So let's do that. This class IO is the underlying framework method that my library is going to be built upon. It has 2 APIs in it. It's got download file as a synchronous version of the API. It's occupying the thread full time. I wouldn't really say it's burning the thread, but it's blocking the thread full time. So it really has a synchronous API, and it's synchronous underneath. The next version, download file async, is not. It's using task.delay, so it's got an asynchronous signature and an async implementation. This one is true async. Now let's look at my library code. In my library, I figured, for whatever reason, I wanted to write a library that exposed an asynchronous API. However, for some reason, for whatever reason, maybe I just didn't know that the operating system had an async version, or maybe the operating system didn't have the async version when I first wrote this library, so I had to use the synchronous version of the operating system. And the only way that I could expose my library method with an asynchronous signature was by wrapping a call to the operating system inside task.run. All it's doing is downloading the file and then printing something on screen. And then let's look at what happens when the user hits the button click method. In this particular case, this user had the expectation, he didn't just want to call the library helper function once, he wanted to call it 100 times. And he looked at the library method, he saw that it had an async signature, he thought that it fulfilled the async expectations. He thought that he could just launch it, say, initiate it 100 times, so that all 100 times would run in parallel, and then he could await task.whenAll to pick up when they've all finished. Well, let's see how that pans out. Start it. I'm going to hit the run button. And it is doing them all. It's fetching all 100 files. But it's doing something quite bizarre. It's doing this batching. That is totally not what the user expected when they invoked our library API. They didn't know how our library API was implemented. And the reason is, what's happening is that each time it invokes my helper method, it's calling into task.run. It's using the thread pool. But the thread pool, my laptop has only got 4 cores, so the thread pool only starts with 4 cores. Then it looks, and it says, after about a second, it says, hey, you're making crappy use of the 4 cores. You're using all 4 threads of my thread pool, but you're not doing anything with them. They're all idle. So it says, I'm going to try and inject another thread in. And that's why, if we run this a second time, we can see the first batch, it did 4. The next batch, it did 5, because it injected another thread. The next batch, 6 of them. So it was slowly growing up, gradually, to find the optimal number of threads to run this workload. Can you tell me what is the optimal number of threads to run this workload? This 100 requests? It's 100 threads. And if it's taking 1 second at a time to inject each new thread, it would take 100 seconds before it had reached the optimal number. And that would just be crazy. I think, really, the way to look at this is that as the app author in this sample, I only saw the signature of the library method. I did not know that any threads were involved. And really, the way I see it is that the threads and the thread pool are an application global resource. They're under control and responsibility of the app developer. If you're the library developer and you start using them in an inconsiderate way, you're treading on territory using a global shared resource that's not yours to mess around in. You should not be doing that because it's breaking the expectations. Let's fix this up. Let's imagine if instead of this, we'd done it properly, we'd used true I/O, so it was async all the way through. Sorry, not async, it should be await. And if I run it this time, hit the run button, brilliant. It's able to kick off all requests immediately and wait for them all to finish at the same time. So that's what we've got to. I mean, the app developer is expecting that he can just kick off the work on the UI thread, and as the library developer, you don't want to be the guy who violates that assumption. And really, if you're using task.run inside the library, you are putting up roadblocks that prevent the user of your library from optimal use of their thread pool. So what that means basically is that in general, unless you're doing something special, some library that explicitly has something to do with background threads, if you're just doing a general library, you should not be doing task.run yourselves. You should be letting your callers do task.run. Because, as I said, the thread pool is an application global resource that you should not be stepping in. And in a server app, we already talked about that, spinning up threads hurts scalability. We totally saw there how it hurts scalability here. And also we talked before about why it's bad. And especially one thing to think about, let's suppose you've written a library and it's multiple method calls deep. And somewhere deep inside your library, you're using task.run. Maybe you're just using it in one corner case, not for all of the cases. And then if the user is using your library from some kind of server code, and they happen to trigger this case, they're going to get really hard to diagnose perf problems. They're really not going to be able to find out where, because they had so little insight into what your library is doing. So that means it's really important that your libraries should be through and through true async, if you're going to use async. And really, the application is the person who's in the best position to manage their own use of threads. Your library should provide synchronous methods that block the thread and do CPU work, and should provide asynchronous methods that are true async, and leave it up to the application author with his own domain-specific knowledge to figure out how best to manage those threads. Well, that's the general rule. There are a few exceptions that I want to talk about. One of them is WinMD files. The point about WinMD, I mean, the whole reason you're writing WinMDs is probably because you want to expose your library in a Windows 8 app to JavaScript developers, let's say. JavaScript does not have task.run. JavaScript authors have no way of creating a thread to run your CPU-bound work. So in that case, you're basically going to have to create an asynchronous wrapper around your CPU-bound work that just calls task.run internally. And basically, that's what the Windows API has done throughout. The Windows API has lots of CPU-bound work, like encode PNG, clearly a CPU-bound work, but in the Windows runtime, it's an asynchronous method just so that JavaScript developers can call it. And the guidelines in Windows is if a synchronous piece of work is going to take more than 50 milliseconds, then it should be asynchronous. Actually, what we find with our true async is that 50 milliseconds is an eternity. Most of our true async methods will be completing within a millisecond or less. There's one other case where we're going to be doing task.run inside our libraries. And this one's a bit subtle. Let me paint for you the picture of inside. When we're building the .NET Framework 4.5, we have the base class stream. And in .NET 4.5, we introduced a virtual method stream.readAsync, because some streams, like file stream or network stream, really should have a read async method. But not all streams will implement read async with true async. Maybe we have some streams that were written back in .NET 4 where they didn't even know about this method, so of course they didn't override it. Well, if the base class stream has got this virtual method stream async, it has to provide a baseline implementation of it in some way. And if it doesn't have anything better it can do, the only thing it can do is call the underlying stream read method. So internally, the base stream.readAsync does task.run on the underlying stream.read method. So it's doing everything I told you not to, but it's doing it because it had no other choice. Well, the reason it has it there is because we really wanted read async to be a method on the base stream type so that everyone could use it. Now, certain stream-derived types do override it with much more efficient implementations, like file stream, network stream, I already mentioned, have got true async implementations. Actually, even memory stream implements it much better. You ask yourself, how can memory stream implement it better? How can memory stream have a true async implementation of read async? The answer is it doesn't. The answer is, question, how could we implement memory stream.read async in a good way? Well, one option we have is to do task.run to do a synchronous read on a background thread. The other way that we actually do implement memory stream.read async is with the synchronous copy of memory from one chunk into another, because that's what read async has to do ultimately. And it's more efficient for us to just copy it directly rather than spawning a thread to copy it directly. And we can copy it directly like lightning fast. It doesn't take any time to copy from one chunk of memory to another. So that got a bit deep. But the overall message there is that generally we're not going to be using task.run inside our code unless there are particular reasons. And one of the key reasons is that your API or your class hierarchy just demands it. That was what we talked about async methods. We talked about the user's expectation when they see async and how we can fulfill it. I want to talk about the converse side, like when the user sees a synchronous signature in your API, what does the user expect of that? Well, they're thinking a few things. One thing they're thinking is that if there's a synchronous version, then I bet it's faster than the asynchronous version. I bet there's a real reason why they offered it as well as the async version. The other thing they think is that they can invoke it from their UI thread just fine as long as they have their domain-specific knowledge. Like, if they know that the list has only got 10 elements, then they know that a synchronous sort of that list will happen quickly enough that they can do it in their UI. So if they see a synchronous version of your API and their knowledge tells them that it's going to finish quickly enough, then they're going to feel free to invoke it from their UI thread. And the question we're going to ask is, suppose I've already implemented a true async method in my library. Should I also offer a synchronous facade around it, a synchronous wrapper that just kicks off the underlying async implementation and waits for it? Well, no. There are problems with that. And I want to do a demo to talk about what those problems are. Let's just close all this. Go back to my second demo. Go to definition. Actually, the demo, I want to do a demo in a different thing. Sorry, Store app. I want to do a demo in a Windows Store app, so it's got a user interface. In this case, I've done exactly what I just described. I had a library with a true async method, async signature, and it's async under the hood. And then I created a synchronous wrapper of it. Maybe, why did I do this? Maybe I did it because I thought, hey, some of my users will want to just call a synchronous version. Maybe they don't want to use await. Maybe they want to call it when they're not in an async method. I'll make it easy for them, so I'll do this. Well, what happens in this code is that the user hits a button click. It's going to invoke the synchronous version of the API because they haven't written an async button click handler. And let's run this and see what happens. Actually, what happened is that the user used their domain-specific knowledge. They knew that the thing was only going to take half a second. They thought it would be fine to just call that synchronously. It won't be too bad on my UI. So they call it. And look at that. It hasn't just blocked for half a second. It's blocked indefinitely. This button is still in its pushed state. We've really violated the user's expectations here. What's happening? This is the deadlock that we really need to avoid. What's happening is that the user called foo, it got in here, it kicked off foo async, it kicked off task.delay, and then it did await on it. So it asked for the remainder of this method to finish half a second later on the same thread, because that's what's important about await. It resumes where it left off. So it's asking it to continue where it left off on the UI thread. But meanwhile, next thing we do when we got to the first await of this method is we get to the wait and we block the UI thread. So the UI thread at this stage is unable to do anything. It is unable to resume this method, and that's why we've got the deadlock. And the reason for this deadlock is that we put in the wait here. We shouldn't be doing it. Really, what we've done is we've been abusing the contract that we had. When the user saw that there was a synchronous method, they thought they could call it safely, and we abused that. I mean, if we offer a synchronous API in our library, the user isn't going to say, oh, sorry, it's my fault for calling it from a UI thread. I should have known that I was only meant to call it from the thread pool where it would have been okay. They're not going to think that. They're going to think this is a stupid API. And this kind of deadlock is going to happen whenever you expose a synchronous method from your library which calls task.wait or task.result. You're just inviting deadlocks when the user calls it. And the lesson there is let your callers wait. Don't just expose a synchronous version. If you've already got the async version, don't just expose the synchronous wrapper around it for symmetry to make your API user. That really is violating the user's expectations. Users will expect your API to operate without deadlocks if it looks synchronous. And the reason what we saw is that doing sync over async, that is wrapping async inside this synchronous wrapper using wait or result, is very likely to lead in deadlock. We're going to talk more about that deadlock in a bit. But I want to sum up where we got to. We said your job, a responsible library developer, is to make sure that your APIs don't lie. If they look sync, they should be sync, not just wrapping up something async under the hood. If they look async, then they should have an async implementation under the hood. And the user will look at the name of your method to guide them in all of their expectations and all the ramifications that come with it. I like the phrase responsible library developer. It makes me feel proud. That's the first part of the talk. The next third of this talk, I wanted to talk about the different environments that your async methods might be called from. What do we mean by environment? We'll get to that. But really, the context in which your method is called will become critical, and we will strive to be writing library methods that are agnostic. They work fine if they're invoked from the UI thread or from the thread pool. Part of what I'm going to tell you in this section is that you should, whenever you, inside your library method, rather than just awaiting something, you should be doing await something.configure await of false. And we'll learn what that means and what it does. And we'll also be talking about another part of the calling context called execution context. The first context I want to talk about is synchronization context. Synchronization context is a kind of esoteric framework, corner of the .NET framework. It existed in .NET 4, but no one used it. No one used it because it was full of bugs. Now with the async language support, we're using it all of the time under the hoods. A synchronization context represents a target for work to be done. In other words, it gives people the power via its post method to do work in a particular place. What do I mean by that? Well, if you're writing a WinForms app, there's the current synchronization context is what's called Windows form synchronization context. And when you invoke .post on that guy, what it's going to do is control.beginInvoke, because that's how WinForms manages to shift work onto the UI thread. If you're doing a XAML application, Windows 8, WPF, Silverlight, then the current synchronization context is going to be this one, dispatcher synchronization context. God, who's ever heard of these things? But in this case, if you invoke the post method on it, under the hood, it does dispatcher.beginInvoke, and we recognize that as the way in our WPF applications to push work back onto the UI thread. There's also an ASP.NET synchronization context, which is what it does to make sure that each asynchronous step of your page gets done sequentially, one after the other, that it never runs in parallel. There are about 10 of these in the .NET framework, and sometimes if you're doing advanced stuff, you'll be writing your own synchronization context. And as I said, synchronization context has become the core way that await resumes where it left off. What do I mean by that? I mean, if the user writes await task, the first thing it does when it executes the await operator is it captures whatever was the current ambient synchronization context. Then, later on, when the task is finished and it resumes after the await, it calls sync context.post on that sync context that it captured in order to resume after the await, quotes, in the same place where it left off. So, if you called await from the UI thread, it will resume back on the UI thread. If you called it from the thread pool and you do an await, it will resume back on the thread pool. Maybe on a different thread in the thread pool, but still somewhere in the thread pool. This resuming where you left off, in application level code, it's almost always the right thing to do. It's almost always what you expect. Like, I've written a button click handler, I await for a file to be loaded off disk, and then I update the UI with the results, or I data bind them. I really do. I'm grateful that I've resumed where I left off. But for library level code, this resuming on the sync context is almost always the wrong thing. So, what we're going to do whenever we use await inside our library methods is we're going to use configure await. We're going to, if we've got a task of any sort or an asynchronous API, we're going to await download async.configure await of false. Await file.open async.configure await of false. Now, false .true is the default. That's what it normally does. And if you just want true, meaning resume on the synchronization context that I captured earlier, you don't need to do configure await. It's only if you want the non-default behavior of not resuming where you left off, of not even capturing where you left off, that's where you're going to use configure await of false. And really, the message here is to use configure await of false in all of your code. Why? There are two implications of it. One is performance. If you do this in your library code, it will avoid unnecessary thread marshalling. We'll see why that is. And the other reason, it's going to avoid unnecessary deadlock. Let's go to a demo of this. Let's, where am I? I want to get back to my other demo. And I want to do a demo about capturing the context. Go to definition. I'm going to do all of my little perf demos the same way. I'm going to do them over a number of iterations, in this case 20,000 iterations. And I'm going to explore two different ways of writing a library method. One is using just await on its own. So this one is using the default behavior. It's capturing the synchronization context before the await and doing sync context.post to resume on it after the await. So this one's called with sync context. The other one is doing .configure await of false. And we're going to explore the perf differences between the two of them. Well, when we run it, I'm just doing a warm-up here, just to explain why this line is here. It's because I want to do any warm-up, jitting the code if necessary, before I start doing serious perf measurements. And then the perf measurements will start here. First we'll run it with capturing, and next we'll examine the .configure of await a false version. So let's run that. I'm going to hit the run. There was a 14-fold difference between the two versions. I was doing, how many was it? I forget, 10,000, 20,000, 100,000 iterations. I don't know. But the one that just did the plain old await T had about 14 times as much overhead. It took a full, that's almost 0.8 of a second more just on the overhead of capturing and restoring the synchronization context. This one, about 0.6 seconds were taken just capturing and restoring the synchronization context. How many iterations did I do? 20,000. Okay, so it was 0.6 seconds difference to capture and restore over 20,000 iterations. That's not much. I mean, it's just a few microseconds. And it's completely irrelevant, this difference, if you're just doing a small number, like 10, 100, a few hundred, 1,000 in your library method. But if your library method is going to be called by your user in a tight inner loop, then this is going to add up fairly quickly. So you have to be careful. You have to figure out, will your library method be called in a tight inner loop? If so, that will be a problem, and you should configure await of false. And actually, if we stick to doing configure await, it's also going to help avoid the deadlock problem we saw earlier. This is really interesting. I'm going to follow through this step by step so we're clear on what was happening. This is what should have happened in an ideal world. We have a user who calls await download do work async, and do work async was a true async method. But let's suppose the user this time, let's suppose the user did the wrong thing. They called .wait on your method. What happens in this case? Let's go into the right or wrong of the user calling a blocking call on your async method later, but let's just step through what happens. First, they invoke it on the UI thread. Next, it goes into here and task.run schedules some work to run on the thread pool. Then we come to the await operator, so it captured the current synchronization context, and it hooked up a continuation to run when the task completes. Then it returns to the caller, and the caller is doing this blocking call to wait. A few seconds later, the thread pool work finishes. It completes on the thread pool, and then it invokes the continuation, which does sync_context.post to get back to the UI thread. And as we've said, the UI thread is still blocked, and that's where we got the deadlock from in this case. But what happens if we're done configure await of false in this case? What was the difference? Well, a key difference here is that await no longer bothered capturing the synchronization context. The next difference is that task.run, it completed on the thread pool, and then it invoked the continuation, the console.writeLine of done task. It invoked the rest of the method, but it didn't bother forcing itself back onto the synchronization context where it left off. It didn't bother pushing itself back onto the UI thread. It resumed wherever it happened to be, if possible. Where did it happen to be? In this case, most likely it happened to be on the thread pool. So it just resumed on the thread pool. And because it resumed on the thread pool, it was able to finish the method. And so the user's call to do work async.wait was validated. It was fine. There was nothing wrong with it. Well, one question to ask about this. You think, this is weird. I am finishing off my method here on the thread pool, and then I'm returning to the user. Doesn't that mean that the user is going to resume their work on the thread pool? Generally, no, it doesn't. Why not? I've forgotten what I was going to say for that reason. No, I can't remember. Oh well, it doesn't matter. Sorry, I'm just a bit lost in my talk. What I actually wanted to do was do a demo of this to show you just really concretely that the demo disappeared. Let's go back to this user interface demo. Remember, in this case, the user was invoking button click, and it was calling library.foo. Let's suppose, really, the user had done library.foo async.wait here. So here, it's not the library that was at fault for wrapping it up inside the terrible thing. It was the user at fault for calling wait on a blocking thing. And here, if we just do this code, it's going to have exactly the same deadlock. But suppose that I'd implemented it with configure await of false. And I run it. Then this is going to do exactly what I just talked through in that slide. So I'm going to click the button. Half a second the button was pressed. It was blocking the UI thread for half a second, but the UI thread became free for it to continue where it left off. And that's why we say, as a library author, get into the habit of always using configure await of false. Really, the reason for this is because the user's thread doesn't belong to you, it belongs to the user. If the user's writing code on the UI thread, they don't want their UI thread polluted with your library method posting back to it all the thousands of times. They don't want any of that. They want your library method to just do its work quietly, not bothering the application's UI thread if it's not necessary. So, as a rule of thumb, you should have in your library methods always use configure await of false on every await. There's one other part of context I wanted to talk about, execution context. This is an even more esoteric corner of the .NET framework. This is a sort of ambient context that contains general information, like the currently logged on NT user, if you're doing impersonation of some sort, or the current culture information, if that's important. And what's important about this is we should think about it as a kind of alternative to thread local storage, because we know that thread local storage is a way of keeping ambient context in our thread. But if we're doing any number of a whole different other ways of doing work, of delegating work to be done somewhere else or at some later time, we can't use thread local storage mostly, because where we're putting work to do often isn't running on the same thread. And that's where execution context comes in. Execution context is an alternative to thread local storage that works against all of these points. The reason I'm bringing this up is that in async methods, the execution context has internal optimizations to optimize it for the default case. If you haven't disturbed the execution context, then awaits are going to run quicker. What implication does this have for us as library developers? Well, if we're a library developer and we've created a library where we're storing information in this execution context, just to have ambient information as a convenience for us, maybe like we're doing some async aware version of transaction support, We can't use thread local storage for that. It has to be in execution context. If we're doing that, that's going to have a small perf impact on every single await that happens while we have data stored in there. Also, if we're creating an API where our expectation is that the user is going to use ambient execution context to store their data, then it will run into the same problems. I want to show a demo about this, of what happens if we modify the execution context. We're still in my Windows app. Let's get back to my other demo. Go to definition. And we're going to explore the difference in performance between code where the user has captured stuff in the ambient context versus when it's still left in its default state. Here I'm doing how many? 1 million iterations in this particular demo. And the work I'm doing isn't much. It's just a million times awaiting task.yield. What does task.yield do? Task.yield is an API that has no use in your finished applications. Its only use is in unit tests and in doing this kind of test or demonstration like I am. What task.yield does is when you await task.yield, it does return back to the caller, but then it schedules its continuation to resume as soon as possible or whenever convenient, or something like that. It's a bit like application.do events from the olden days, but it doesn't necessarily do all of the events it needs to do. So that's why it's kind of dodgy and not worth using in production code. Anyway, what I'm going to do is I'm going to store some information in the ambient context. Logical call context data store is just a dictionary from string to object, so I can store anything I want in it. And I'm going to start the timer. I'm going to do my work and measure it. And then I'm going to free this named slot. And after I've freed it, it will be back to its default state. Therefore, we can take advantage of the optimizations inside this async that are triggered when you've got the default optimization context. Let's run this code and see what it does. What we can see is that the code that modified the execution context is taking 60%, 100% more time to run than if we hadn't modified the execution context. Like here, when I was doing 1 million iterations, it was adding about 0.1 of a second to it. That's not a huge deal normally. Like a few tens, a few hundreds, a few thousands of awaits, this extra thing is not going to have any impact at all. It's only if your asynchronous method in your library is going to be called inside a tight inner loop that this perf difference is going to add up. I want to just show you something here. Question: why would a user ever use one of these terrible blocking APIs like task.wait after we've seen how bad it is, after we've seen that it leads us to deadlock? Well, async is really a virus. If you start using an async API right at the bottom of your program, then its caller is going to have to await it. And because that caller has got an await operator inside it, that caller is going to have to be marked async and change its name to async. And because that caller is async, that method is marked async, then its caller in turn will have to await it and so be marked async, and so on, all the way up. If we want async, if we want true async, it naturally bubbles all the way up to the top of our program. That's the ideal world. None of us live in the ideal world. We live in worlds where we've already got some framework or some architecture where something has already been set down. Maybe we're making a plug-in to some existing architecture, or maybe we're just a small team as part of a bigger project. And they've designed their API 2 years ago, before async and await. So they designed their API to be completely synchronous. And now if I'm using async down here in a corner of my code, I'm going to have to bridge the gap somehow. I'm going to have a call to .wait in it, just so I can be consumed by that top-level synchronous framework. And what I've got here is a console application, an example of a framework that was laid down 10 years ago for .NET that does not exist. It is not possible to write async void main as the entry point for a console application. Actually, we should really be calling it async task main async, shouldn't we? Because we know what best practice is. But that doesn't exist. The entry point of a console application, this bigger framework we're part of, is required to be synchronous. Therefore, we had to put this gap inside it by calling wait. And that's why it's so important, whenever we're writing APIs, that we use that configure await a false trick, so that where they have to, users are still able to block on us. All I want you to do there is to consider the trade-offs. Sometimes you're looking at ambient state and you're thinking, my API will be 100 times more beautiful and more elegant if I can just let the user store information in the ambient state, like transaction support. That would be beautiful if only the transaction team had made one that used execution context rather than TLS. So there are lots of cases where execution context will make a more beautiful API. And the only places where you have to worry is that if the user modifies it and they have a tight inner loop with millions of awaits inside it while the execution context is modified, then it will start to have some kind of perf impact. So you might just consider, is it worth changing my API so I don't rely on, of course, I'm not relying on thread local storage already, so that I don't also rely on global execution ambient state, and instead I ask the user to pass state explicitly around wherever it's needed. In all, for the second part of the talk, we've discussed these various ways where library methods might be called from different environments, and you really have to be aware of them. The most important rule of thumb in your library methods, always use configure await of false. It will help in so many ways. And then we touched on the trade-offs involved in modifying execution context. The final bit of this talk I want to talk about is perf. We've already seen cases where perf is critical if you're called inside a tight inner loop. And I want to talk about more aspects of it. And all of it is going to hinge around this central thing that we call the fast path of async methods. Let's, actually, before we get that, let's step back. We've all written async methods, of course. We all know how cheap, we've all written sync methods, and we all know how cheap they are. Like, here I've written a simple sync method. If I look at the IL, I know IL isn't a perfect measure of how costly something is, but it's a fair enough proxy for the moment. It's doing just what it says on the tin. It's only doing what I expect to. I know that sync methods have negligible overhead, and so I'm very confident that I can just refactor my code arbitrarily and factor out into like a 2-line synchronous method and call it as much as I want. The same is not true for async methods. Here I've got the same kind of thing, async task simple body. I should have called it simple body async, of course. The IL that this one generates is a bit bigger. And this isn't all of it. It generates this code, but it's got this call to something called moveNext, and it also generates this much IL for the moveNext method. All of this is plumbing that's needed to make the await operator work properly, to enable to make a method that can be resumed at any time you want. And if we highlight it, we can still recognize that small part of code that corresponds to what we actually wrote, but there is a lot of boilerplate. There's even boilerplate for try blocks around it, just in case the method ended in a failure. If the method ends in a failure, then the resultant task has to end in a failed task state. So there is going to be a lot more work. And what I want you to have by the time you leave this talk is I want you to have a good intuition, a good feeling for just how much overhead is there. How much do I have to worry about it? Let's go to another demo. We can see that okay. I'm going to have a demo where I've just got an empty body of my async method. So I'm going to be looking at the overhead associated solely with the async overhead. Here's the synchronous version. And here's the asynchronous version. No differences, except I remembered to use the async suffix this time. I put on the no inlining flag just because I don't want any magic to be done. I want to have a clear apples for apples comparison. And what I'm going to do is do this comparison 10 million times. Spin them up once just to make sure they're working. And then I'm going to have a loop where for 10 million times I'm going to try doing the empty body, and then 1 million times I'm going to try doing the empty body async. I'm not awaiting it. I don't need to await because this time I know that there are no awaits inside method. Therefore, even though it's an asynchronous thing, it will still complete synchronously. But let's see what the overhead in this case is. I'll try it a few times. It's funny, the first one was a 40-fold difference, 40-fold overhead of having async, but that was just a first-time startup method. The actual true figure, 13, 10, about 10 times the perf. It's taking about 1.5 seconds of overhead to do all of that boilerplate we saw for 10 million iterations. Once again, think to yourself very, very clearly, 10 million iterations is a lot. Everything I'm talking about perf here is irrelevant if you're just calling the await thing 10 times or 100 or 1,000 or 10,000. It's only when you start to get into the tight inner loops that we're going to worry about it. And actually, what that tells you is you have to be pretty careful about tight inner loops when you're making library methods. If you're making a library API that encourages the user to do tight loops, then you're going down the wrong direction. If your library had a method called getNextByteAsync for reading a gigabyte big file, it will be called a heck of a lot of times, and you'll be running smack bang into the middle of these problems. What you should do instead is to try and design not chatty APIs that are called really frequently, but chunky APIs that are called less frequently. Like, rather than get next byte, we could get next batch of bytes, next 1,000 bytes or something like that. So the mental model you have to have is that the async methods do have a bit more overhead than sync methods, and think before you go async. I just wanted to be clear, right? I've been talking about these overheads. These are not overheads particular to our compiler implementation of the await keyword. In fact, we've done a pretty jolly good job of implementing await as quickly as possible. And if you try to call async APIs using some other ways, using callbacks manually, you're going to find that your code runs slightly less efficiently than what we've got with the await operator. Why is that? Because we really have people in the CLR team who know every last bit about how the JIT operates. They could micro-optimize the heck out of it. And also we could rely on internal functionality in the task type to make it run quicker, which won't be publicly exposed. So await is doing the best it can. And it's pretty good most of the time. But you need to keep aware that there is going to be some overhead. We're going to look at just how much overhead. In fact, let me do that. Let me go back to this demo. Here, the figure was about a 10-fold difference in overhead. What I'm going to do is put this back and put an empty for loop. I don't know, 100. Let's try 50 first. With an empty body. So my synchronous version is just going to have a for loop 50 times, nothing special. And let's run that. Run it a few times. 0.8, 0.9, they're about the same. What that's told us is that the overhead of invoking an async method is about equal to the cost of doing an empty for loop 50 times. So 50 integer additions, 50 integer comparisons. That's not much. You normally wouldn't think of doing 50 pluses and comparisons in your code. And that gives you a scale for how costly we should think that async is. I want to talk about one final aspect of perf, and that's to do with garbage collection and the heap. I don't know if you went to Dustin Campbell's awesome talk yesterday. It was essential truths everyone should know about performance in .NET. The main message he had there was that performance is really strongly related to how much memory you allocate and how much the garbage collector has to run. The more you allocate, the more the garbage collector has to run. That's what's going to slow your app down most of the time. Actually, in .NET, allocating the objects is really cheap. It's the garbage collection that takes time. So we want to minimize allocations as much as possible so the application need to have fewer garbage collections. And we should think about this the same way as we were thinking before. We talked about how the thread pool was an application global resource that we're swimming in and we shouldn't mess around with it too much. We talked about how the UI thread belongs to the user. It doesn't belong to us. Therefore, we're not allowed to deadlock it. Also, we should think that the memory of the computer belongs to the user and we shouldn't be using it too much. We're swimming in the same pool. We shouldn't mess it up. And what we're going to try and do is avoid unnecessary allocations. And I'm going to show you how async methods avoid those unnecessary allocations. Because there are a few optimizations that are actually built in that really are fantastic. First, the plain truth that we're fighting is that whenever you invoke an async method, it involves allocations. It involves 3 allocations. First allocation is for what we call a state machine. This is like a display class that holds the local variables. The local variables that were inside your async method have to be turned into fields of this state machine class. And so we have to allocate an object on the heap containing all of those fields, all of your local methods. Next, it has to allocate a delegate, because that delegate will be invoked when the task that you're awaiting finishes. And next, an async method returns a task, right? A task is a class object. It's not a structure. So it's going to allocate a task on the heap as well. Now, the smart thing is that if the method skips all of its awaits, then it bypasses the first 2 allocations entirely. That's really significant. You might ask yourself, well, what kind of method would skip its awaits? If it's not doing any awaits, why the heck is it even an async method? Here's a pretty good example why. Look at this. Get next in async. I know I told you not to do get next byte async. This one's different. This is get next int async. But I'm doing it because I wanted to show you a really useful general technique. Underneath, it's going to fetch next buffer async, which probably fetches 1,000 integers in a batch. So it's only going to go to the disk or the network or whatever once every 1,000 integers. But that means that 999 times out of 1,000, it saves the whole chunk inside buff. 999 times out of 1,000, it will already be there. It will see that we've still got space left in the current buffer. So we're just going to increment it and return what we've got left. So most of the time, this method is going to return immediately because it hasn't encountered any awaits. Therefore, it's not going to incur the first 2 allocations. But it's still going to incur the 3rd allocation. And is there anything we can do about that? Yes, there is. If the method does this all the way through without having to suspend on any awaits, and if the return type was, say, if the return value was something, one of the primitives, like 0, 1, true, false, null, the empty string, what we did is, in the .NET framework, we have a singleton for each one of these. So if you return 0 at the end, it will just return that singleton. Why is that? Because an already completed task is immutable. It's indistinguishable from another instance of an already completed task with the same value. So we can just reuse them as much as we want. So that's beautiful. If it's one of these simple types, we can do that. It's not most of the time, though. It doesn't make sense to allocate a singleton for every possible task of integer. That'd be quite a lot of them. Or task of string, there'd be even more of them. So for other return values, you'll probably want to cache them yourself. And we'll talk about that. But before we do, I want to talk about another beautiful optimization inside async methods. If the awaited task has already completed, this is what the code gen for the await operator looks like. It says first something get awaited. Then it says if the thing has already completed, if it hasn't already completed, then we do all of that suspend and resume and allocate memory and sign up continuations magic. But if it has already completed, we can skip that and just get the result. In the past, I've been telling you, how does an async method behave? I've said it goes through up till the first await. When it gets to the first await, it returns to the caller. I wasn't telling you the truth. What it actually does is it gets to the first await which has not yet completed. And only when it gets to the first await which has not yet completed does it return to the caller. So if the awaits in your async method have already completed, then it will just run straight through this fast path, straight to the end of the async method, bypassing a bunch of allocations. You might think to yourself, okay, that's fine, but seriously, in his right mind, what kind of async methods would already be completed? Like, if they're async, isn't that because they take a long time? Well, no. The one I just showed you on the previous slide was an async method that has already completed 99.9% of the time. So this kind of thing is taking really good advantage of that. It all composes well. I'm going to show you just one final demo. This one's really beautiful, using all of those optimizations. Read async.run. Here, just doing 100 iterations, but what I'm doing is copying 1/4 gigabyte of memory. And I'm going to compare, and the way I'm going to copy it is using the new copy to async method, which was introduced in .NET 4.5. And I'm going to compare the performance of two different implementations of memory stream. One of them, we're calling copy to async, so we know that copy to async is going to have to call the underlying stream.read async under the hood. And my first implementation of stream.read async just does the synchronous read and then returns the value. So it's using the fast path, but it's not caching the return task. Because every time you read, I happen to know that copy to async is copying in chunks of about 80K in this case. So first time you call it, it's going to create allocate a task object with the number 81920 inside it. Next time you call this async method, it's going to allocate another task object with the same number inside it. Every time, it's going to allocate a new task object. Let's look at the next version. This one has a cached task. So, what's going to happen is that when someone reads it, we're going to find out how many bytes we've read, and if our cached task was cached for the same number, 81920 most likely, because when you do copy async, you just allocate a buffer and you keep doing it with the same size. So every single time you're going to ask for the same amount to be read. Then we return the cache task without allocating anything new. Let's run this and watch the perf difference. The first version to copy that quarter gigabyte file 100 times had to do a garbage collection 14 times. The second one only had to do it 4 times. So by caching the return task, we've dramatically reduced the amount of objects we're allocating on the heap. So this is a really useful perf tip if you're going to be called lots and lots of times in a tight inner loop. I just want to show you, I know I'm over time, I'm going to go for one more minute. I want to show you something neat. We compared these two things. Let me compare you against the memory stream that's actually built into the framework. Again, the first one took 14 garbage collections, and the memory stream in the framework took 0 garbage collections. So somewhere inside there, the CLR team have optimized the heck out of this method. And it's possible in general with async. You can dig down as deep as you want to make the optimizations you want. If it's going to be called a lot of the time, often it's not worth it. What we've shown you, being aware of that fast path and caching the result, those are generally enough for you to get the performance you want. And just what we saw is that we wanted to cache the task of T, because our whole goal was to avoid allocating another task, because it doesn't do any good just to cache the T. And the other thing we did was that we've actually found most of the time that a cache of size 1 is the right size to use everywhere. Well, that's the end of it. It's been very clear from what we've talked about that your goal should be using async wisely and figuring out where to use your async APIs. First, be true to what you advertise. Be true to your signature. Use configure await of false. Take advantage of the fast path optimization, and if necessary, cache the return task. That's everything. I really hope that you're going to go out and write some reliable, robust, and performant async libraries now. I'm going to be around here at the Visual Studio booth for the rest of the day and the Ask the Experts table in the evening if you want to chat further. I'd love to have more discussions with you. Also, one final plea, please fill out the evaluation forms. If you liked it, fill them out. If you didn't like this talk, fill them out. I deserve to know either way. Thank you very much.